right, hello everyone. So let's get started with today's lecture, and we are going to continue and conclude inflation. Yesterday, after the lectures, I got several questions, so I decided to expand a little bit the discussion about inflation, and I'm going to give you a few more details, okay? But before arriving there, also during that session, I got, after the lectures, I got, again, questions about energy conservation in GR, right? You see now the concept is important. And I just wanted to recall you the idea of redshift, because of the redshift that we have seen, that I discussed in relationship to photons, but it can apply to any other species in the universe, also matter. The fact that the density, the energy density of the matter is going down as a to the minus 3 is redshifting of matter in that context, okay? Anyway, if you recall, when we introduced redshift, right, I was basically looking at the relationship between the time clock of phenomenon, an event, for example, a transition in the emission lines in an atom, at the observer, and the time clock for at the emission time. Okay, that's the ratio between the two, and everything was basically linked to the metric. Okay? Right. And I never spoke about velocities, ever. Okay? Then you can interpret, yeah, okay, the universe is expanding, and therefore I can also think about the redshift of photons in terms of the fact that galaxies are going further away from me. But the very nature of the effect is on the fact that the metric is time dependent. I give you another example. Let's take photons coming this direction. Let's imagine that there is a clump of dark matter, and dark matter do not interact with electromagnetic radiation. No interactions. Therefore, it doesn't touch the photons at all. And it makes its own life, like it evolves. And let's imagine that there is a density dense enough to collapse, right? Under its own weight, right? The dark matter particles can collapse, pull together one with each other through their gravitational, mutual gravitational interactions, G. Okay? Then what happens? As they are falling one to each other, they gain kinetic energy. And you're going to get a point in which the kinetic energy is going to be roughly the potential, equilibrium. Okay? You get particles that are kind of with very complex orbits, but you get a stable object, which is virialized. That's called the virial theorem. That is used to describe this very simple scenario. What happens as the particles are getting together to the gravitational potential? So imagine we start with a loose over density. The potential is going to be very flat. If the structure gets denser and denser, the potential gets deeper and deeper, the gravitational potential. Now let's imagine our beloved photon that is traveling this direction, and the structure is virialized. You know that we have the time clock, which has a different rate, because of gravitational redshift. Okay? And when the photon is coming here, it's going to be blue shifted, because it's going in a depth of the potential. It's like the ball which is rolling down. It gains energy. When we are at this part, it gets redshifted. And the amount of blue shift and redshift is the same, because in the end it's an integral of this curve, the net effect. How is it going to look like? What is the frequency of the photon? It's exactly the same as the beginning. Now let's imagine that the structure, that this is happening while the structure is forming. What's going to happen? The photons enters with a gravitational potential of this depth. Therefore, it gets blue shifted by a bit. And as it goes through, the potential gets deeper, 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 and deeper. Therefore, the going up is kind of climbing up a potential that is deeper with respect to the entrance time. What's going to happen now to the photons? To the energy of the photons. Here is going to have a frequency. Here is going to have another frequency. And the frequency of the outgoing photons is going to be smaller with respect to the frequency of the incoming photon. Sorry, the way around. Okay? Nu prime is lower energy. It's redshifted. What was moving here? What was moving here? This photon was emitting on a galaxy here. It has nothing to do with what happened on the way. You see it better now? So everything is due to the fact that G mu nu has a time evolution. There are no velocities involved here. Okay? And the photon didn't interact with dark matter because there is no electromagnetic interaction with the dark matter particles. The only thing that happens is gravity. Gravity changed. G mu nu has a time dependency. Okay? Right. Good. So let's continue with the discussion about inflation. Close this parenthesis. And before going to further details that I promise I'm going to give you, first let's get an overview of the picture of everything, okay? And as you know, the dynamic of the universe is ruled by the equation of state parameters. This guy here. For a scalar field, this expression, once we plug in pressure and density is equal to this quantity. Let me use U, since I always used U, is equal to that. And according to the fact that the kinetic terms is dominant, for example, then the equation of state parameter, W, is equal to 1. And we have that the density of this fluid is evolving as A is expanding with the power of -6. If phi dot square is roughly U, that's equal to 0. W equal to 0, rho is directly proportional, so there is a pressureless fluid, and rho is directly proportional to minus A to the power of -3. If we are the way around, in which we have phi dot square, so the kinetic term much smaller than the potential, W is equal to -1 plus an epsilon, where epsilon is a positive number, and much smaller than 1. So W is a little bit larger than W, the -1, and the expansion, A, and then we get a fluid that is constant. So it's E to the power of 0. So there is no density evolution. That's why the inflaton field is not destroying itself. Its density is not dropping to 0 as it is expanding in this crazy way. All the rest get basically erased. Their density dropped to 0. The inflaton density remains constant during the inflation time. Key difference, okay? And the rho is roughly constant. And we have an expansion that is exponential. Exponential expansion. Very violent. Nice. And basically, all this kind of stuff explain how the universe is evolving. So just W, right? Just to continue with the field, because here we used matter, but if we have a relativistic fluid, this could be relativistic massive particles or photons, the equation of state parameter is e to the power -1, and the density goes e to the power -4. This is just to complete the picture. Okay? So what we have seen is that during inflation, we have the slow roll approximation. So we start with this one, accelerated expansion. Then we enter a phase of oscillations. Or if you want, we can have a phase, not always, but we can have a phase of fast roll. in which we have this evolution, and then followed by a period of oscillations, harmonic oscillations, damped, as we have seen, with an equation state parameter that is therefore W equal to 0, and it's matter dominated. Then we have seen that afterwards there is a reheating phase in which we included in the equation of motion of our fluid, phi dot dot plus 3h phi dot plus u prime equal to 0, where we included an additional term to allow the production of particles. So we have seen that by introducing this, we have the friction term, which is given by the expansion of the universe. This thing here. Okay? General relativity, no particle creation. So the drop in the density, right? It has kinetic energy that is slowing down. That kinetic energy is lost because the universe is expanding. This is this concept. For the production of particles, we need to introduce this new term. And then I also told you that this term can be related basically to some interactions that you plug in into the Lagrangian, right? So we can have an expression of this friction term, which is an interaction term maybe of this sort. Sorry, V square and then C square, where we have the interplay between the field and matter. Okay, so they must talk one with each other to transform one into each other. If in the Lagrangian you have terms that are independent, field and the field and matter, they don't talk one with each other. You need to introduce this guy into the Lagrangian. And then you get your interaction. You say there is a L interaction, which is a function of phi, and C, two fields. Then you can build it up as you want. But that's the idea. All right. Then what I'm going to show you today, that's this additional information I wanted to give you, is the fact that we have an energy release from the field to the medium. Okay? And we need to consider what happens to the temperature. That's important. That's extremely important. Because it has huge consequences on the universe, on the life of the universe, as it follows. Because if we have this sort of expansion, you understand that even if we had particles at that time, very fast expansion, where goes the temperature? It plummets to very, very low temperature because it's an adiabatic expansion. Okay? Therefore, if we want to explain the baryonic, the Big Bang nucleosynthesis, which basically give us the formation of helium, other like beryllium and lithium, few traces, starting by free protons, okay, we need high temperatures. High temperatures, and that's for the Big Bang nucleosynthesis. We are going to see this process that happens when for temperature of roughly 1 mega electron volt, so pretty high energies, where we have basically individual protons that there is a chain of reactions. Now I just make it simple. There is also deuterium involved in the process. There are various stages that this happens, but bottom line, we are going to have free protons and a fraction of them, and we have the prediction of the fraction of how many of these protons can go and form helium-3, helium-4, and as I said, some beryllium, and then some lithium as well. And this takes place after inflation. Okay? So you understand that to have these high temperatures, the reheating process is crucial, because here we have the kinetic energy of this guy that is transferred in the particles. And if we have, for example, this process, which is given by a self-annihilation of the field, giving two particles as products, there is a kinetic energy transfer here. Okay? And if we compute the energy, the temperatures at the reheating time compared to the typical energy of the particles of the standard models, we find out that this energy is much smaller with respect to this one. Of course, in this case, energy, right? Energy momentum, and we are talking about energy momentum conservation for the reaction. We're not talking about GR stuff, okay? These are just equations related to this sort of reactions and particle productions and annihilations. And you understand that if this is going to be their mass very small, where is the other energy which is transferred? Kinetic energy. High velocities, high kinetic energy, high temperatures. We have an increase in temperature, reheating phase. Ha! We get temperatures that are now high enough to explain a field of all of those particles, extremely hot, that cools down because then at a certain point the expansion continues. And when the temperature is low enough, they can start to merge. Can start to interact effectively, they're not anymore photo-dissociated, and we have the production of heavier elements. Okay? Now we are going to compute this temperature, among other things. Okay? You have a question? T, reheating. REH, reheating, call it as you want, is the temperature of the reheating phase at the end when we got the maximum temperature of the particles that have been created. Okay? Just to make clear all the various steps, let's give a look at this plot. In which you can see all what we just said, okay? So I'm not going into details here because, I mean, I already gave them in abundance in the past. So we have this phase of accelerated expansion for the slow roll. We might have a fast roll expansion. And in general, and the thing that is crucial is the reheating phase. So we have this damped oscillation where the additional term is going to release particles. And the story continues, and it's this one, okay? So that's basically what already depicted at the blackboard. We have a slow roll phase where we have the inflation. The inflaton is the ruling species, and the dominant term in the kinetic equations describing the equation of motion of the field is the potential equation of state -1, and that's the temperatures that we have. Here, the reactions are not efficient. Because we have two time scales in place, right? If we go to the equation here, we have this h, which is a 1/time. And we have this tau, which must have the same units, and is what? A reaction rate. Is how many reactions you have per units of seconds. And this instead is the units of time for the expansion of the universe, meaning from how particles are diluted away, are brought away one from each other. And you see that these are two competing processes, right? The particles want to meet, reaction, expansion, they are brought away. And if the expansion rate dominates with respect to the friction term, to the reaction time scale, then the reactions are not efficient because the particles are brought away and don't have enough probabilities, not enough time to merge and create the reactions. Okay? Then let's skip fast roll. Phase is not that important, but then we have the oscillatory phase, and that's very interesting because, again, we start at the beginning where the inflaton is the ruling species, so rho phi is the guy ruling the expansion of the universe. That's the condition, for the oscillations, potential similar to the kinetic energy, and once we get the average of the effective equation of state parameters, we get a zero expansion that I already explained. Now, this starts to be, at the beginning, we are still kind of inheriting this phase. Nothing with respect to the reaction are taking place. But afterward, the particles start to play a role. And we have the transfer of energy to the particles. And you have the two densities that are starting to change. Okay? Remember that here the density inflation is constant. Here the fluid, so the inflaton, is behaving as matter and is redshifted. Now its energy density in this oscillating phase is going down. Plus it's transferring energy to the particles, so this dependency is going to acquire an exponential term here. Maybe I will derive it. Okay, I will show you. So maybe I will include it here as well. So from this phase, we have this one plus an exponential cutoff that is due to the combination of the expansion of the universe, this one, plus the exponential cutoff, which is the transfer density that goes in something else. Nice. And here, now, yes, we start to have this equality. When that's the case, then, because we have the transition from an expansion function to so gentler expansion, then this starts to be important. The reaction rate is efficient, is similar to the two time scales are similar, and then reactions can take place. Yes, they are drawn apart, the particles, but they have time to meet and do reaction things. Okay? Nice. Let's see where in the overall cosmic epoch all of these, let's finish also the end of it. Because then, at the end, once we have this transition, the inflaton is consumed, and what are left are relativistic particles with high temperature, as I mentioned, and we are going to compute them. With an equation of state parameter, which is 1/3, that give us the beginning of the hot Big Bang, what is called the hot Big Bang. So we start with the Big Bang, that back at the time had extremely high temperature. So it was ruled by extremely high energy processes. And once the inflaton is gone, then also this ratio takes this is going to take place once the reaction rate ruled basically over everything and the inflaton is dead. Now we have a radiation-dominated epoch. Whoop. And that's what we could talk about. So all of that I explained happened here. Please. These are seconds, okay? These are seconds. Look the thick from here to here. We are at 10 to the minus 35 seconds. So we are talking about a process that took an instant, okay? That's all the stuff happened in that very, very, very beginning of time. And again, you see what's the meaning of time. It depends on the stages of the processes. Is h large, is tau large? Doesn't mean anything. You say large or small if it's comparing with something else. Same goes with distances. What's the meaning of space? Doesn't make any meaning. I can tell you the space between these two hands. If I remove the hands, how do you define a distance? Okay? Good. So time scale, which are extremely fast with respect to our day, but they need to obey this sort of rules, nevertheless. So we have basically the field at the beginning. We have the inflationary stage. Then we have the reheating, which is in this little blip here. And then we start with a standard radiation domination expansion that will continue afterward with the matter domination expansion, which will continue afterward with the dark energy dominated region. Now we are in the in-between matter domination and energy density domination. Okay, so that's the sequence. So the first part of the lectures was about this story. Now I spoke about this mini millimicro, mini tau, picoseconds, or whatever it is. Yeah.
So the pass-through is potential dependent?
Yes, yes. All the inflation, as I showed you, it depends all on the potential. So everything is extremely model dependent. That's why there is not a consensus on inflation in the sense this is the model, because you can play with the potential and you can use different reaction terms, and the reaction rate depends on the strength of the coupling. Okay, so you can play with a lot of things. Yep.
Is that
Sorry? Yes, yes, exactly. That's the grand unification time. Yes.
That's just grand unification.
Yeah.
So is that where we say the transport decouples?
Yeah, basically yes.
Okay.
Yeah, well, they start to decouple. Yeah. But the timing is really, you know, it's really loose. And again, the looseness is due to the fact that we don't really know. We don't have strong evidences on picking up one potential or an interaction rate with respect one with respect to another. Okay.
Put it within inflation, regardless of what model we use, we always say that like the transport decouples.
Yeah. I mean, you're going back in time, you have those high energies, and that's what you would expect. Okay, all right, what did I wanted to say then? Okay, that comes later. Good. Let's continue with inflation. Yeah.
So in the plot which you just shown, we started at 10 to the minus 45 seconds.
Yes.
Like the beginning of the plot. Is there a specific reason why we choose this time?
Yes, because that's where our understanding of physics stopped. Because we are basically, you see, everything was based on general relativity, you know, the expansion of the universe and so on, everything general relativity. And this is not a quantum mechanical theory. It's a classical theory, it's an effective theory. And whenever you go at those high energy and these very, very tiny scales, then you need to account for quantum effects. And there, to describe those epochs, we would need quantum gravity. And at the moment, there is not a really functional theory for quantum gravity. Therefore, typically you go at the Planck time where gravity should break. Okay, so everything starts from the Planck time because of this reason. All right. So let's start with a few more details about inflation. So if you recall, I gave you an example of a potential, which was U of phi equal to 1/2 mass of the phi power of 2, and then phi to the power of 2. So just a parabola with, as you see, U of phi equal to 0 for phi equal to 0, right? So the potential is 0 at the minimum. U, phi, and we are here for the reasons I explained you, to avoid because it's a very simple model, and we don't want to have remnants of a cosmological constant that would destroy the universe, for example, okay? Nevertheless. Then we used our equation of motion, and we used the slow roll approximations, and we arrived at this expression that then we solved. You see, we have a phi dot, and we solved it. We made our integral, and we found an expression for the evolution of the field as a function of time, which was phi e 1 minus t over tau, where tau was a function, well, let's write it so that you have it, of phi e square root of 12 pi g over the mass of the field. And I told you that here in this tau we have a combination between a ratio, basically this tau depends on the ratio of the mass of the scalar field and the initial condition values of inflation. Right. Now, let's give a look a little bit of this phi e term, the initial condition for our system. Phi e. And let's see how we can link it to the number of e-folding. Last time I told you that it's possible to do it, now we do it for real. So we go for the number of e-foldings. I recall you that they are just the definition of the ratio between e some other value, reference value, that's the initial value at inflation, and we just take the logarithm of this thing. That's the number of e-foldings. Therefore, the change in the number of phi folding is related to h dt. So we just make the derivative, and that's what we get. Then what we can do is to use our equation of motion, where we have our h, you see, this expression perform an integral, so that we have a relationship between the expansion function given by the dynamic of our field and the number of phi foldings. So we have our equation, this guy, and it's equal to v prime, right? So we bring the v prime on the other side, we get a minus, and then, just to be explicit, the v prime means derivative of v with respect to phi. Remember that v is a function of phi. You're using that model. All right. Now let's work out the left-hand side. So let's work out this guy. And we want to express it in forms of dn. Therefore, we want to express this phi dot as derivative of phi with respect to n. And that's simple. This is just the phi over the n over the t. Then we can plug in our then, so that we have a closed expression with respect to h. So we obtain 3h to the power of 2 phi prime, where prime now is the over the n, okay? Not over the phi. Okay? The over the, I don't know, I could use some other symbol, but then get messed up. Okay. Then what we do, we have our Friedman equation. And we plug it here. Our Friedman equation gives us, the factor of 3 is the factor of 3 that we have here. Then we have the Friedman equation, which is 8 pi g over 3. And then we have and then times v. We derived that in the previous lecture, and this was due again because of the slow roll approximation that is involved in everything. And the potential, now I make it explicit, is this one. So that's the Friedman equation. This is our u. Okay, and then we have the n over the t. So we have a lot of stuff that cancel out. So this one goes away, 2 and 8 becomes a 4 here. And yeah, that's it. Or the phi, yes, you're right. Phi. And phi. Well, it's phi of t. I mean, yeah, no, you're right. Sorry, I messed up. Phi. And then give us a 1. And this gives us a 1. Because we have m squared, because we have so we brought the v. We have then, so this is the first term, this one, and then we have this guy here. And this is just the derivative of the potential that we are using. We have the minus, because we brought it on this side, and then we have m squared over phi. And we have m squared, p squared. Yeah, that goes away. And sorry, then phi and this one. Sorry? is t. Then of t, I can do that, because then is a function of t, so that's fine. Then it's just the Abel law. And this is the phi. Okay. Wait, sorry. I'm messing up everything here. So that's Friedman. What the hell? What am I not getting? Then over the t. And there is the phi prime missing. Should be a phi prime. Let me do the computations. That's the phi to the. That's the phi over the n. The phi over the n. Yeah. Did we manage? Okay, great. Fantastic. Okay, so this was the left-hand side. And then we have the right-hand side, which is this one, where I just, again, plug in the definition of the potential. That's it. Well, I used U, so let's stick to U. All right. Now you can see I just have at the end of the phi, and I can basically solve it by separating the variables, and I perform the integral. Therefore, we have 4 pi g phi square over 2 minus phi initial to the power of 2 divided 2, and then that's equal to minus n. And then we have 2, and this becomes a 2. Nice. Look, phi e. We have the condition for the initial conditions that we said we can set it, again, everything to keep everything very simple, when phi is equal to 0, meaning when the pendulum is swinging and we are at the maximum kinetic energy, there the thorough condition is broken. So we get before we start to swing like that, okay? That's the end of inflation. We mark it just like that for simplicity. If we do that, then our n is equal to 2 pi g phi e to the power of 2. That's just this expression. And look, we have an observational constraint. Because that's the number of e-foldings that are needed for explaining flatness, to explain the homogeneity of the CMB, so the horizon problem. And then, as a byproduct, to explain the relics that get washed away. We have a constraint that is coming from observation on phi e. So we have this condition that phi e must be larger to the power of 2, we have a power of 2, larger than the number of e-folding times 2pg. Observations. Fantastic. We have a condition that tells you that inflation is working in this way and gives you the right number of e-folding whenever this condition is met on phi. And I'm using that this has to be larger than that because the constraint that we did the last time were starting by assuming an error on the observations, right? Flatness nowadays had to be between 1% with respect to the 0. That's an observational limit. And then we traced it back in time with the theory and asked for how inflation should have been. Okay? So that's the maximum that it could be. Okay? Can be smaller. We don't know. That's why there is this inequality. All right? And now look at this phi. So this phi e is crucial to get the inflation that we want. Now we can go back in time, because so far I told you that we're using rho. But rho, in reality, is the background that we described, is the average, because we made an approximation. Keep in mind always the approximation that goes along the way, because what we did was to use the Lagrangian of a scalar field, and in the derivation, there are terms that depend on special derivatives of the field, okay? D of phi. Go back to it. You will see that there are terms that were equal to that, but then we drop them because we assume homogeneity, anisotropy, no gradients, no fluctuations, assumptions that works on large scales, meaning on averages, on volume averages. Now, if we break this assumption, we resuscitate, or I don't know how to say, you keep them, you bring them alive as little Frankensteins. This guy is active and we have fluctuations. So you have a field where the values of phi are different in different locations. Okay? So if we go back at the time, we have phi that depends on time, because it does the thing that the field does, and we have a special dependency. That's important, because if we think that we are starting from a vacua, so we are starting from a field that was at the ground level, we have our quantum fluctuations, and the quantum fluctuations are exactly given by this term here, okay, macroscopically. Then what happens? That we have regions across the universe where the values of the field was different in different locations. And we might have a location where that condition is met. Whenever phi e is larger than this phi e minimum that is down in that equation, then this one is going to inflate as an inflationary bubbles. The other ones might inflate, but maybe not enough. So they keep a curvature, and if they have a curvature which is, if they start with an hyperbolic geometry, they would inflate. It's going to be an open universe, not ours. If the phi dot is the way around, is on the other side, and the curvature is not, for example, is spherical, then the universe will be recollapse. Okay? So we have different regions in this initial field where we can have, where this condition is not met, we can have universe that quit and recollapse. Closed geometry. The inflation is not lasting long enough to give the accelerated expansion and bring the curvature to zero. If you start with a curvature which is positive, spherical curvature, that region is going to do like that. If it's hyperbolic, then it will expand forever. But with a rate that is not the one that is needed for our universe. So this guy set the conditions, and you can picture that phase of the universe as something like that, this bubbling pot, this bubbling quantum pot. All right. The other bit that I want to go into are a bit more, a more detailed derivation to evaluate the temperature of reheating. And to do that, we need to make a little bit more mathematics, a bit boring, a few steps are boring, but that nevertheless is interesting to see how we can get the temperature of reheating. All right, so where do we start? We start with the equation of motion. We are studying our system, and the equation of motion tell us how the system is evolving. We include our interaction rate, and then we have the potential, the derivative of the potential, that's equal to 0. All right, then we need to solve this equation, and we do something simple, meaning we start by multiplying times phi dot. That's what we do. We multiply for phi dot, we get phi dot dot phi dot plus 3h phi dot to the power of 2 plus u prime phi dot plus the reaction rate times phi dot to the power of 2, and again equal to 0. Now we do something again simple, which is to look at this guy here. Look, that's the derivative. This is the time derivative of phi dot to the power of 2. So note, we have phi dot dot, which is equal to 1/2 d over dt phi dot to the power of 2. Right? Make the derivative, the 2 comes away, cancel with this one, and we get a phi dot dot, which is this guy. Simple as that. Then we look at this other guy here, and we realize the fact that is actually v prime of phi dot is equal to the u of phi with respect to the t. So we have these two guys that are two time derivatives. We can put them together. So we get d over dt of phi dot square 1/2 plus u of phi, and then we have the rest. 3h phi dot to the power of 2 plus reaction rate of phi dot to the power of 2. Look at this. What's that? This is rho phi. Remember, from the scalar field? That's the density of a scalar field. So now we are transforming this expression into an equation that is referring to the density of the scalar field. Nice. Therefore, we continue. That's the time derivative of this rho phi. Therefore, we have rho phi dot plus 3h phi dot squared plus the rate of phi dot square, and that's equal to 0. Oof, we are almost there. There are these two very annoying things, phi dot. Okay? Now, if we want to link this phi dot to the density, such that we have a full expression that depends only on rho, we need to do a little bit of machineries. And to do that, we need an explicit expression of the potential. So far, we just have a u, and that's it. It's completely model. I mean, we still don't have to specify the model. To proceed further, we need to specify a model. And we are going to use our simple parabolic potential. And we are going to study the field in this approximation. The mass of the field much larger than h. What does it mean? That we have the rate of the pendulum rate, the frequency of the pendulum, which is much larger with respect to h. Okay? That's the meaning of it. So that's fast oscillations, if we want to call them like that. All right. Nice. In this approximation, we basically get phi dot dot plus m squared. That's the mass of the field, of course. And times phi, that's roughly 0. So you see, we are dropping the other terms, only the mass is the ruling one. And we are just working on the natural frequency of the pendulum, avoiding the two friction terms, okay? That's again to get some analytical solution. Then we multiply times phi, and we need to make an average, which is a time average. Okay? So if we do that, we have a phi dot dot. And we are doing this average because imagine we have the pendulum and it's swinging, okay? But you know that it slows down and then it starts slowly. So we have an equation of state. Fast, we have a different equation of state, slow, and so on and so forth. So what we need to take is an average, a time average over many pendulations. I don't know what to say, oscillations. Better to say, okay? So that's the meaning of that. Plus m phi, which take it as a constant, and then we have phi to the power of 2. The power of 2, again, because we multiply by that, and that's equal to 0. Now let's make the average. So we have phi dot dot. So what we need to do, what is an average? If I have an average of a finite number of values, then I make the summatory of the values and divide by the number of values. If I have an infinite number or a continuous distribution of values, I substitute the summatory with an integral. And I divide by the two integration limits of the integral. So what we do for the integration rate, you know, you have the average of some number, I don't know, let's call it I don't know, A. And this goes from E equal to 1 to n. And then we sum values, E of E. And of course, we normalize it with the number of values. Whenever you have a continuous distribution of values, the summation goes from some value minimum, so T min in our case, and T max. And then we have our function of time integrated with respect to time. And now what we normalize? We then normalize with respect to the time interval, because it's the average in that time. Okay? So that's our transition from a discrete to a continuous distribution for the averages. That's nothing very deep, but that's how it is. So what we do, then we have 1 over t, where with t I mean this difference. So that's the entire time interval that we are considering. Between 0 and t, I can always shift the time as I want, right? It's anyway, what matters is the difference in time. And then we have phi dot dot. This is the function that I'm integrating. That's the integrand. And that's the integral in the t. Okay? So then I cut it short. You can make this integral. And what you find the steps in the note. And in the end, you get that this guy is equal to that. I want you to keep stick to the concept now. Is averaging over integrals that are done like that. Here I gave you the step from discrete to continuous ways of making averages. Okay. Then this is just a matter of solving this trivial integral between 0 and t, and that's the result. All right. Now that we have that, we can replace this guy with that. So we have phi dot squared plus m phi to the power of 2 of phi squared is equal to 0. And with that, we just bring, there is a minus, where is the minus? Because integration by part. There is my minus that is popping up, okay? Here there is an integration by part. Okay, you integrate by part, you get a boundary term that is equal to 0 minus this guy. That's where the minus is coming about. Okay, you will see it in the lecture, in the notes there is the step. So we get phi dot, let's do it here, m square average phi to the power of 2. And with that, we get our expression for our scalar field. Because rho phi, you know, is to be equal 1/2 phi dot to the power of 2. Now, keeping in mind that we are talking about the average. Now we are a little bit more rigorous. Plus u, what is the potential? Is our parabola. 1/2 m to the power of 2, and again, phi power of 2, averaged. And the 2 1/2 goes away, in the sense they sum together and they give us a 1, and we have the final expression, which is this one. We have the link between the density and phi to the power of 2. Yes, that's the phi dot. Okay. Now that we have that, we can go back to our expression and replace it here and here. Now we have an expression with respect to the density of the scalar field. An expression which is just rho dot phi plus 3h rho phi equal to minus phi, and then the average of phi. That's what we have. You want to know how many particles of inflaton field you have? That's easy, because the number of particles of the inflaton field is just the density of particles divided the mass of the field. That's how we associate the density to the number of particles, just by dividing the energy density with respect to the mass. This gives you the number of particles with that energy. Okay? So you see, it's easy to transform this expression. You basically divide this expression by m phi, and you get the evolution in number of the inflaton particles. So what is our full system of equations? Okay? So look, here there's no any shocking physics happening. It's just a way, I just did the steps of solving this differential equation. So we are just using this expression. The only tricks that are going on are just mathematical tricks to arrive at this expression, such that we can start to introduce the density for the field. And then here we are using this approximation. We are using this approximation, and we are performing an average such to have a relationship between the density of the field and m phi to the power of 2, which is needed here. Okay? With that, we have all our equations with the full system. Let me write it here. We have rho dot phi plus 3h rho phi equal to minus, now I'm bringing the reaction rate on the other side, rho phi. That's the equation that we derived. What is missing? What is happening here? We have the reaction rate. We are creating particles. We need another equation, which is derived in the very precise way. But now we don't have the field. That's not the density of the field, but it's the density of the radiation field. That is ultra-relativistic particles that are created. We have a new component that is playing. And you get 3h rho plus p, actually, equal to minus phi rho phi. Here, in the expression, we always dropped the pressure of the field because it was negligible, because we are on a matter-dominated epoch, remember, where pressure is equal to 0. But for baryons, that's not true, because the pressure is 1/3 rho c to the power of 2. I mean, when c is equal to 1 is rho c. And it enters here. So these factors together gives you a 4h rho once you plug in that. Okay, let me write it. Rho dot of radiation plus 4h rho plus p. That's always radiation equal to, plus reaction rate phi, and then rho of phi. Yes. Sorry, guys. Rho radiation equal to plus phi rho phi. Also here there is the pressure, So the full expression would be this one. But this is equal to 0 because we are in a matter-dominated epoch. So the guy is, the inflaton is behaving as matter, pressureless. This gives you a 3. Relativistic fluid, this gives you a 1/3 rho, which sum up gives you 4h rho r. And then we have the expansion of the universe. H to the power of 2 is equal to 8pg over 3 rho phi plus rho radiation. That's our system of equation that one needs to fill up. So for matter, we have that h is equal to 2/3 t to the power of -1, and an accelerated expansion, which is equal to a0 t to the 2/3. All right. Then let's give a look what is the real expansion of the universe at this time, including the reheating. And we start, of course, from our equation of state. So let's see density evolution. Density evolution of rho phi, including reheating. Okay, for simplicity, every time we said a to the power of -3. Now let's be a bit more precise and include the reaction rate into the game. So again, back to our dynamic equation, and we plug in what? We plug in the h that we expect at this time. These are all approximations, because look, here we are going to get an expression for the expansion function that is not for matter only. So by neglect, we can neglect rho at the beginning for the fluids. Sorry, for the radiation component. We have only this field, and we are assuming that at the initial time we have a purely matter-dominated universe, meaning that h is going like that. That's an approximation. Okay, so we are going to first order to get a correction to that. It's not valid all over the time. Okay, just to show you how then this one is going to play the game here. Then what you do? We just perform an integral. So our rho dot is rho dot phi over rho phi equal to minus 2t to the power -1 plus the reaction rate in the t. And we just made the integral. See, it's just this guy. We perform the integral. T of the rho and the t. That's it. What do we get in the end? We get rho phi as a function of time for this very beginning, rho phi, which is at the initial time, e divided e to power of, e to the power of -3, and then we have an exponential. See, we have an exponential because we have this integral of 1 over function, give a logarithm, then we make the logarithm, the exponential of the function, and this is popping up. Again, very trivial integral. That's what you get. So you see, in the end, if we, at the very beginning, where, yes, the h factor is roughly like that, but if we account for this, we get a density evolution for the field, which is not perfectly like matter, because reactions are anyway there. Maybe they are subdominant still, but they are there. And there is this exponential drop. Okay? These are all approximations, okay? But this is to show you that then the evolution, the real evolution of the density is changing. You want to do it precise, then you need to solve this integral in full power and in full glory. Okay? You need to solve the system of equations without the approximations, and you solve that in full glory, and you get the full expression for the evolution of the density, including the reaction rate. All right. Good. Next step would be the derivation of the temperature of the reheating, but I'm out of Blackboard. So we can have a little break. We can resume at 30 past. I clean the board. And I'm going to give you, again, using this framework, we are going to derive the temperature of reheating. So we are going to see the temperature that we are going to have after inflation ended and after reheating. Okay? And that's the key for all the following physical processes. On top of that, I'm going to show you, because we discussed now that we have this bubbling situation at the beginning. We have the value of the field that once we break the approximation for perfect homogeneity, there are tiny fluctuations at the quantum level. And I'm going to show you how it is, due to inflation, these quantum fluctuations that act on quantum level length scales, they get stretched on macroscopic scales, which can be this one, this one, this one, our galaxy, and in between galaxies. So from a microscopic separation between particles, we are going to macroscopic scales. And this sets the seeds for the following evolution of the matter distribution, radiation distribution, dark matter distribution of our universe. That then is going to follow the laws of gravity and collapse, form galaxies, form filamentary structures, forming galaxy clusters. So now, later, I'm going to give you the seed for the formation of the cosmic structure. All right, so as we said, 30 past.